Hey everyone, so I want to continue with pretty much the last thing that I want to mention about linear motion in particular, and that's the idea about acceleration. So far we've talked about how we can measure how far an object moves by talking about the distance and displacement. We talked about how fast an object can move by the rate at which it covers that distance. Now the next thing that we want to do is, well, how quickly can these speeds change? So that leads us into this idea about acceleration, represented by an a, which is defined as the rate at which the object's velocity changes. Now I wrote in here speed as well. That's just because sometimes you might see a problem where they're not giving you velocities because the object's just going in one general direction. So you can kind of also simplify it to just be the change in the speed, but technically it's change in velocity. And important thing to note is that the acceleration and velocity are not the same thing. They are very similar, but they describe completely different concepts. In fact, there are many cases where the velocity could be a maximum value, a very large number, but the acceleration is very small, and vice versa. So don't think that just because you have a high velocity, that necessarily means you have a high acceleration. The units for acceleration are meters per second squared. So again, you want to be able to recognize this unit and immediately think acceleration. Once again, acceleration is a vector. I had given you a list of all the vectors before. Acceleration is another really big example of a vector. And like with all vectors, it has magnitude and direction. So one thing to note is, what does it mean when an acceleration is positive, when it's negative? So if we mention that acceleration is positive, that usually means that the object's speed is increasing in the positive direction. So it doesn't necessarily mean that the speed is increasing, but that it's going in the direction of positive. And that the idea is that the object wants to start going positive. So if the velocity was originally positive to begin with, and there's a positive acceleration on top of it, that means the object will be speeding up as it continues to increase in that same direction. But if the velocity was instead negative and we had this positive acceleration, now what we have is different directions. That negative velocity is going to start to decrease as the object starts going towards the positive, starts increasing into that positive direction. So it's going to end up slowing down until it either comes to a stop, or if that negative acceleration persists, ends up reversing direction, which is why we say it's tending towards the positive direction with a positive acceleration. On the flip side, if we had a negative acceleration, again, using a similar definition, it means that the object's speed is decreasing in the positive, or another way of putting it is that it's increasing into the negative. Same thing. Once again, if the velocity was initially positive and we have this negative acceleration, that positive direction is going to start to decrease as the object slows down, and again, eventually starts either coming to rest or reversing direction. If the velocity is negative, though, it's going to maintain that negative direction and is actually going to speed up. Now, altogether, the big takeaway is that the direction of the acceleration and velocity matter, in the sense that you want to note whether or not they're the same direction or opposite directions. If they have the same signs and they are pointing in the same direction, then we're going to have a case of an object speeding up. If the acceleration and velocity are in different directions and have different signs, one being positive, one being negative, then we have an object slowing down. This is really the crux of it, because in a lot of these questions, you might not even be given specific directions. You might be just told that the object is going in a direction, but then they mention that it's slowing down, which you're supposed to take away is that the acceleration is now negative. That either when you do your final calculation, you should get a negative acceleration, or you should make sure to note that the acceleration in the equation is negative. So this is why I want to make sure that I stress this idea about direction mattering. And like I said, you really want to make sure to kind of take this to heart. First, we're going to start with the most basic equation, and this is actually the first equation on the reference table for the AP. It's v equals v naught plus at. So the v is representing the final velocity, v naught is the initial velocity, a is the acceleration, and t is the time. So for the most part, you see this equation, plug the numbers in, get an answer. So here's a first question. Pause the video, work yourself, and we'll go over in a second. All right. So they want to know the direction of the acceleration. Now, the key phrasing here is decreasing speed. So when you read this question, you see the word decreasing speed, your mind should immediately realize that velocity and acceleration have to be in opposite directions. The next thing to take away is that the car is originally driving south. So the velocity is south. Because velocity and acceleration have to be in opposite directions, that tells me that the acceleration has to be north. All right. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so for here, let's start pulling out in the information. So here we have an object that's initially traveling 3 meters per second towards a wall. So v naught is going to be 3 meters per second. Then it says it bounces back at 2.8 meters per second. Now, if I make a mistake in how I note this, I could end up getting the answer wrong. Now recall that the acceleration is the rate at which velocity changes. So the v and the v naught have to represent velocities. And as I mentioned, velocities carry direction. They're vectors. Direction matters. Now you might be reading this question and thinking, how can we get direction? Well, direction doesn't necessarily mean north, south, east, and west, or left and right. This is a direction towards the wall and away from the wall. Even though it doesn't say away, it's implying that. So those are now our directions. So we're going to define towards the wall as being positive. Therefore, the final velocity, which is pointed away from the wall, is now going to be negative. So when I record that 2.8 meters per second, I want to record that as a negative 2.8 meters per second. Continuing on, the time is 2 seconds, and we're looking for the magnitude and direction of the acceleration. So what we're going to do is use our equation, v equals v naught plus at, plug our numbers in, and we get the acceleration is negative 2.9 meters per second squared. Now, the 2.9 is my magnitude. The negative is giving me direction. Now, I can't, because the question doesn't specify what is defined as positive and what is defined as negative, I technically can't leave my answer like this. So I would actually have to, once again, use the directions given to me in here. Once they didn't say anything about north, south, east, and west, or left and right, so I have to use the phrasing of towards the wall and away from the wall. Because of the fact that the velocity, the final velocity, was defined as negative 2.8, and this number is negative as well, that means the acceleration and the final velocity are in the same direction. So I would say that the acceleration is 2.9 meters per second squared. And then I would say that it's away from the wall, because that's what the final velocity is doing. Away from the wall. All right. Now, this was a thought question that I had posed to people was try to think back to a time when you experienced acceleration. Like, we've all experienced acceleration at some point, and try to think about what does it feel like and how can you tell if you're accelerating, if you're accelerating a lot versus a little. Now, some common examples of times when you accelerated. Clear ones would be driving in a car. If someone speeds up and like steps on the gas, if someone slams on the brakes, those are clearly accelerations. If you've ever gone onto an airplane and the airplane's still ascending or as it's coming down, you should have felt some acceleration. Any roller coaster ride, or typically almost any type of ride like that, you are feeling some form of acceleration. Now, one thing you should notice is that in those examples, if you try to really think about what it felt like to accelerate, you should have noticed that there was this feeling of pressure almost on your body, that your body was kind of pulled in a certain direction, depending on how you were accelerating. If you slam the brakes, your body is pulled forward. If you step on the gas, your body is pulled backwards, and so on. And that feeling of the pressure of the force on you, moving your body in some way, will end up getting stronger the greater that acceleration. So the question is, where do you think that a bungee jumper would feel the greatest acceleration? Now, this link, you can't really get to it, but it goes to a YouTube video by Veritasium about a bungee jumper. And he poses this exact question of which location would the bungee jumper feel the greatest acceleration? He has also videos on all the choices that you could choose from, and all except for one are incorrect. And he gives a brief little explanation of why certain choices are incorrect versus being correct. I highly recommend that you watch it. Normally I'd have it pulled up, but I don't want to put it on this video. Now, in addition to that simple acceleration equation, we have two more kinematics equations that deal with acceleration. I call them complex just because there's a lot more going on with them, but they're extremely useful, and once you get the hang of it, it'll become a lot easier. So the first one is this equation. I call it the annoying x because the a lot if you look on the reference table, there's a lot of subscripts on the v naught and the a, and there's just a ton of x's all over the place. So I call this the annoying x's equation. And then the next equation, this one is the timeless equation, because this is the only kinematics equation that is without time, hence the phrase timeless. Now, a few things that I want to note: you can technically simplify these equations a little bit. So for the timeless equation, you can keep this as v squared equals v naught squared plus 2a. And then instead of this x minus x naught, you can actually replace it with a delta x. This is useful because a lot of the times the initial position, x naught, is going to be set equal to 0. Or you might be in a scenario where you're looking for distance, and it just makes a lot more sense to talk about delta x. Because x's in these equations are representing your final position, and x naught is your initial position. I guess a good way of trying to think about it is that it's almost like imagining or trying to think of the problem, laying out the problem on a piece of graph paper or on a number line. And x naught is where are they starting at on that number line, and x is the final location that they land. Because everything's pretty much relative, you can always kind of move that starting point wherever you want. So if an object starts some distance away from the starting point, but then gets further away, maybe it starts 5 meters from the origin and then moves 10 meters from the origin, you could just move the whole thing over so that instead of starting at 5, it actually starts at 0. That would change the final location. But it doesn't really change anything, it just makes your life a little bit easier. This one could also be simplified as delta x equals v naught t plus 1/2 at squared. So you can use these slight little variations. I'll show you the cases where keeping the x naught actually makes life significantly easier. All right, so here's the next question. Pause the video, work itself, and we'll go over in a second. All right, so we'll start getting all the information. First thing, because the fact that this is a fairly basic, straightforward question, I'm actually going to start off saying that the initial position is 0. Now, the final position, it tells me that it ends up coming to a stop over some 70-meter distance. So I'm going to say that the final position is 70 meters. In addition, I know what the initial velocity is. It was initially traveling at 100 meters per second. So I'm going to record that. Then it says that it comes to a halt. So the final velocity is going to be 0. And then it wants to know the magnitude of the deceleration. So they want to figure what this number is, the acceleration. Based off of these variables, the only thing that wasn't given was time. So I'm going to end up using the timeless equation. Plug the numbers in, and I end up getting that the acceleration is negative 71.4 meters per second squared. Once again, note that because of the fact that this says technically asks for the magnitude, you could have given this as negative 71 or positive 71. you will get the answer right regardless. Here's the next question. Pause video work itself and we'll go over in a second. All right, so there's two different ways to go about this. There's one that's slightly longer and one that's short. I'm going to go over both quickly. So the first thing, again, write down everything that's given to us. The initial position is still going to be 0. They want to know the distance it covered, so it's looking for that final position. Its initial velocity was 10. It slows down to a final velocity of 2, and it's over 4 seconds. Now, using these variables, first, there's not one single equation that has x0, v0, v, t, and x in it. And any equation that we do have all require an acceleration. For example, I almost have enough information to use the annoying x's equation, but I don't have acceleration. I can't use timeless because I don't have acceleration. So what I want to do is put a pin in determining the final position and instead look for the acceleration. So based off of this, I now want to ask myself, instead of what equation can I use to find the final position, I want to ask myself, what equation should I use or can I use to find the acceleration? And the only equation that pops in mind is the acceleration equation, v equals v naught plus at. In this scenario, I have 3 variables and I have one missing one. So when I plug the numbers in, I get that the acceleration is negative 2 meters per second squared. Again, I need to make sure that I note that this is a negative 2. If I don't note the negative 2, then I will end up getting the answer wrong later on. So now I have pretty much any choice of equation at my disposal. I could use timeless or the annoying x's equation. I'm actually going to use the annoying x's equation since it's pretty straightforward. So I plug all the numbers in that I have, making sure that I make that acceleration a negative 2. And I end up getting that the final position is 24 meters. Since I initially said that it started at 0, it means it traveled a total distance of 24 meters. And that's pretty much it. So again, sometimes pay attention to make sure that if you think that you don't have enough variables, then try using other equations to determine those missing variables. Just make sure that you're finding the information properly. For example, if the object is doing different types of motions, then you can't do an acceleration between them. So just make sure that if you're looking for things like acceleration, that it's related to what's going on. Now, I did mention that there was a second way to do this that was quote unquote simpler. As I mentioned before, there's an equation that you can use. It is, at your discretion to use it, but I highly recommend that you try to avoid it as much as you can because there's a lot of issues that could come up with it. What you could have used instead, though, was this equation. The only reason I'm showing this is because you do kind of want to know about it. So you could use the equation v bar equals d over t and have this be average speed equals distance over time. In this scenario, I'm looking for the distance. I know that the time is 4 seconds. The only thing I don't have is my average speed. So I have to actually take the average of 10 and 2. Just like you would take the average of anything, you add them and divide by 2. 10 plus 2 is 12. 12 divided by 2 is 6. So the average speed is 6. Doing this, I can immediately see that I get the same 24 meters that I got last time. However, like I said, the biggest mistake that I always see people make is that they forget that V naught, V, and V bar are 3 different speeds, that they're not always the same. A lot of times people will mistakenly write this as V equals D over T and assume that this V is a final speed. So as long as you can remember that this V bar is an average and you can keep that in mind, you may not make the same types of mistakes. But as I always say, better safe than sorry. Try to just avoid it as much as you can. All right. And that's pretty much it for the acceleration aspect. So now we have three new equations at our disposal, and we'll be able to do some more complicated questions with accelerations in them. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.